Hi guys, just in the last lecture I started integral transform, in which I told you we covered two topics. One is Fourier transform and another is Z transform. And on the last lecture, I just introduced and I told you about Fourier transform. Then I told you if we have a function fx, then Fourier transform is denoted by this, and this is an limit minus infinity e to power minus sx fx dx, and this is naturally after integration, because integration is with respect to x and definite integral limits minus infinity. So after integration, we get a function of s, and it is denoted by factor of fs. This is Fourier transform, and then I defined also a inverse Fourier transform, that is f inverse of f of s is defined as minus infinity to infinity e to power minus sx f of s ds, right? And this is value of fx. This is the inverse Fourier transform. I defined this, and then if you can express by Euler's theorem in two parts, cos sx and sin sx. If you take the real elementary part, then you will get another two types of Fourier transform. One is Fourier sine transform, and like that fs of fx, and this is defined as 0 to infinity fx into sine sx, that is the imaginary part of Fourier transform. And second is Fourier cosine transform. This is defined as fc of fx, and this is 0 to infinity fx into cos sx dx, right? And similarly, you can define the I defined the Fourier inverse Fourier cosine transform and Fourier inverse Fourier sine transform, right? And also I took up some numerical examples directly based on the Fourier transform, how you can find of a given function, a Fourier transform of a given function. And just I was discussing about the after that properties of Fourier transform, Fourier integrals, etc. I defined this, and then I just started and I was discussing in last lecture the Fourier properties of Fourier transform, in which I just told you first property, that is the linear property, in which I told you if we have two functions fx and gx, and take two constants a and b. If we take this linear combination where a and b are constant, fx and gx are two functions of this, and take its Fourier transform, then it will be equal to a times Fourier transform of fx plus b times Fourier transform of gx, right? Means linearly we can expand this. So this was the first property I discussed in the last lecture. Now today I will discuss other properties of Fourier transform. Second is change of scale property. Change of scale property. What is the statement? If Fourier transform of fx is equal to fs, right, then Fourier of f of ax, where a is any constant, if we take this, if in place of x we take ax, this is equal to 1 upon a f of s upon a, right? This is where a is non-zero value, right? This is the change of scale property. Means if directly we know that the Fourier transform of any function of parameter x, and we take the function with the parameter a into x, where a is any constant, non-zero constant, then we can directly write the Fourier transform of this. Means only we have to change in Fourier transform of original function as s upon a in place of s. First we verify this property, how it will be proved, how it will be obtained. As we know that this, then we know that Fourier transform of fx is minus infinity to infinity e to power isx fx dx. Right? This is the basic formula. Yeah, you can say this is the first principle of the Fourier transform. Now, here we have to find the Fourier transform of f of a into x. Now, the Fourier transform of f of x. By this formula, we get minus 20 e to power isx, and here in place of fx is a of x. Now, take substitution here, put ax equal to t, then naturally a dx equal to a dt, and limit does not change, because when you take x tending to minus infinity, then t will also tend to minus infinity. If you take x tends to plus infinity, then t also tends to plus infinity. So this is minus infinity to infinity e to power I s in place of x. This is t upon a. F of t in place of dx means dt upon a. Right? And if you calculate this, simplify this, then you will get your required result. Here you take a outside the integral, then this is minus infinity to infinity e to power I s upon a to t f of t dt. By first equation, we can write it as capital S of s by equation 1, and that is your required right hand side, that is your required result for change of scale property. Right? This is the second property. Now the third property, that is shifting property. Shifting property, similarly, if we take Fourier transform of fx is capital F of s, right? Then Fourier transform of function of x minus a, f of x minus a, this is e to power I s a f of s, right? This is, if we take x minus a in place of x as a parameter, then Fourier transform will be similarly, and this term will be additional e to power I s a. Again, you can verify this. Similarly, we know that Fourier transform of fx is integral minus infinity to infinity e to power isx fx dx. Take this as again equation number 1. Now, we have Fourier transform of f of x minus a. Then by equation 1, by principle, by basic definition of Fourier transform, this is minus infinity to infinity e to power I s x f of, in place of x, it is x minus a. Now again take the substitution. If we put x minus a equal to t, then x equal to a plus t, then dx equal to dt, and limit is again same, because limit is limit from minus 20 to infinity. When you take minus 20 at the place of x, then we get t is equal to also minus infinity. If we take x is equal to plus infinity, then you know that if any term is subtracted by infinity, then will result will again infinity, so t is infinity. So limits will be same. Here e to power is in place of x, there is a plus t, this is f of t, and this is dt. And by multiplication, minus 20 to infinity e to power, this is isa into e to power ist f of t dt, and you can take e to power isa outside the integral because integral is with respect to t. And by first equation, if you see that this term is e to power iss, this term is again Fourier transform of f, and that is denoted by capital F, and that is your required result, that is your right hand side of shifting property. If we take the parameter in sum of this, x of this, and then, right, this was the third property, shifting property. Right, these are the some properties, and the last property, that is also known as a modulation property. If we take parameter in place of parameter, we insert some trigonometrical function, then directly you can obtain Fourier transform if Fourier transform of actual function is given. Right? What is the modulation property? Fourth, modulation property. Similarly, if Fourier transform of original function fx is capital Fs, then Fourier transform of fx into cos ax, cosine inside, then this is equal to 1 by 2 f of s plus a plus 1 f of s minus a, average value of this. Right? This is known as modulation property. Right? First, we verify this. Then, by this modulation property, number of results you can obtain by changing this. If you can take here sin ax and etc. and you can here Fourier. Yes, I will discuss after verification of this property. First, I have to go for verify this property as. Similarly, we know that Fourier transform of fx is integral minus 20 to infinity e to power isx fx dx. Right? This is your capital Fs, and this is your equation number 1. Now, take this one, Fourier transform of fx cos ax. By this property, we have minus 20 to infinity e to power isx in place of fx. This is fx into cos ax dx. Right? We substitute this one, cos ax dx. Now, you know that there is a relation between trigonometrical function and exponential function, and that is a very important result given by mathematician Euler, by which we can change trigonometrical function into the exponential function and vice versa. You know that here cos ax, we can write this is iax plus e to power minus iax upon. This is a standard formula. This is a result obtained by the result of Euler's formula, e to power I theta equal to cos theta plus I sin theta. So by this formula, cos ax will be changed as, this is fx, this is e to power I ax plus e to power minus iax upon 2 dx. Now, this is integral with respect to x, and 1 by 2 is a constant. You can take 1 by 2 outside the integral, and you can open this bracket. Then it breaks into two parts. So Fourier series, Fourier transform of fx into cos ax is given by take 1 by 2 is outside. Then we have two integral minus v to the infinity e to power isx fx into e to power iax dx. If we take, open the bracket and take integral inside, then second integral minus v to the infinity e to power isx fx into e to power minus ix dx, right? And you again calculate these exponential functions, then power will be adding, and then we get 1 by 2 first integral minus infinity e to power I and s plus a into x fx dx. This is the first integral. Second integral similarly minus infinity to infinity e to power I times s minus ax fx dx if you combine powers of the exponential function. Then you see these two integrals and compare with the right hand side of equation 1 with the formula of Fourier transform. So it is the capital F of SA and it is the F of capital S minus A, right? So by equation 1, this is F of S plus A, this is F of S minus A, right? By equation 1. And that is your required right hand side, that is your required result, right? This is the modulation property, this is the fourth property, and all the properties first I proved and verified linear property, then change of scale property, then shifting property, then modulation property. All of the properties I just verify here for the Fourier transform, but all the properties will be existed and will be used by Fourier sine transform as well as Fourier cosine transform. For example, if here we take this for Fourier for cos, then we can also by here we can result Fourier sine transform, right? If we have fx into cos ax modulation property, then Fourier cosine, this is similarly, this is 1 by 2. Only change is that here this is capital F, capital F of S plus A plus capital Fs of S minus A. This is the similar property, only Fourier sine transform is replaced Fourier cosine transform. Similarly, as for cos sine AX, cos AX, and so on, number of results you can prove for Fourier cosine transform and Fourier sine transform on the similar way, right? And all the properties can be verified by Fourier cosine transform and Fourier sine transform. You can try this, and you can obtain similar results for Fourier sine transform and Fourier cosine transform. These are the properties of Fourier transform. Now I will take up some numerical examples, and according to the your curriculum, your syllabus, theoretical part of Fourier transform is completed, and now I take the first numerical example. Find the Fourier transform of fx equal to 1 for mod x is less than 1, and this is equal to 0 for mod x is greater than 1. Hence, evaluate integral 0 to infinity sine x upon x dx. That is very important integral that can be evaluated by the help of Fourier transform, right? And this is the given definition of formula. Then you know that this is the mod value. We can open this because you know that mod x is equal to plus x when x is positive, mod x equal to minus x when x is negative, and mod x equal to 0 when x is 0. So you can open this, minus 1 is less than x is less than plus 1. Alright? This is, and this can be opened if mod x positive, then x is greater than 1 or x is less than minus 1. Right? These are the definitions. So according to definition, first we have to find the Fourier transform, then the formula Fourier transform of fx is equal to, just I told you, 120 e to power isx fx dx. right? So according to given definition of function, this integral will break in three parts, because this is less than -1, this is greater than 1, and this is between -1 to 1. So it breaks into three parts: minus ∞ to infinity e to power isx fx dx, minus infinity to -1, then -1 to 1 e to power is fx dx, and then 1 to plus infinity e to power ix fx dx, right? This integral breaks into three parts. First integral and third integral is 0 because of the definition of fx, because fx is 0. In middle one, that is the second integral, e to power ix fx is 1, and third integral is again 0. If we solve this, you know that integral of isx equal to e to power isx upon is limit 1 to -1. Then this is e to power is minus e to power minus is upon I into s, right? This is the value, and you can convert it into sign by again by using Euler's formula. I have already told you Euler's formula: sin theta equal to e to power I theta minus e to power I theta upon 2i. By this formula, this result will be converted into sine order form. That is, if you divide 2, then 2 upon s sine s, right? This is the final answer. That is the answer of first part of the question, Fourier transform of the given function, right? Now second part, here you have to find in this integral. So this integral can also be calculated, evaluated by the help of inverse Fourier transform, because from here we get inverse Fourier transform, because we know that inverse Fourier transform is integral 0 to infinity e to power minus isx into fs and ds, right? That is fx. By that is fx. This is the inverse formula, and in inverse formula 1 upon 2 pi I also. 2 pi we take this for the rotation of this, right? So here fx equal to 1 upon 2 pi 0 to infinity e to power minus isx. Fs means this value 2 sine s upon s ds, right? This one. And now substitute the given value of function, this one, that is minus infinity. That is minus infinity to infinity 1 upon 2 pi integral e to power minus sx 2 sine s upon s ds equal to fx. And fx is you defined 1 for mod x is less than 1. This is 0 for mod x is greater than 1. Right? This is the definition of function. If we put x equal to 0, then this is 1 upon 2 pi minus infinity to infinity, right? Sine s, 2 sine s upon s, this is 1, and x is 0, this is equal to 1, right? And 2 is cancelled out from here, minus infinity to infinity, sine s upon s ds equal to pi, right? And this is the even function. So by property of definite integral, this is 2 times 0 to infinity sine s upon s ds equal to pi. This implies that 0 to infinity, change the variable in place of s, we take x, sine x dx equal to pi by 2. This is your answer, this is your value of your given integral, which can be calculated by the help of Fourier transform. Right? This is the numerical problem. Here you see that we have a function. First we have to calculate Fourier transform. Then by the help of Fourier transform, we have to evaluate this integral. So you see that here first we calculate integral Fourier transform by the basic formula of Fourier transform, and then we use the inverse of the Fourier transform, and we calculate the Fourier transform. Now we take the another example. Next example, numerical example, that is find Fourier sine transform of e to power minus ax upon x. Right? This is the next example of Fourier sine transform. Previous example, I take question based on the Fourier transform. Here, your numerical sum is the Fourier Fourier sine transform. Means we have to calculate Fourier sine transform of e to power minus ax upon x. We have to calculate this one. Right? Now, by the formula, we know that Fourier sine transform of fx is integral 0 to infinity fx into sine sx dx. That is the basic formula. I have already told you, and we have this is equal to fs. They take this as a equation number 1. Right? Now, here fs of fx here, that is 0 to infinity. Fx means e to power minus ax upon x sine sx dx. Right? And this is, we take fs of s. This is your formula. Substituting the value of this, take this as equation number 2. Now, here you have to see what is the process to solve this integral, because it cannot be solved directly in a very simple method. So here we have a method, we have a trick by which we can solve this integral easily. So first you have to observe this, because integration is with respect to x and s is another parameter. So first we differentiate both sides. We have this. First we differentiate with respect to s. We get, that is d by ds of fs. Right hand side, if you take the derivative inside the integral, then this becomes this becomes with respect to s, and that is partial derivative. So e to power minus ax upon x is constant. Differentiation of sin x is cos sx, and differentiation of sx is x dx. Because it is under sign of integration and differentiating partially with respect to s. This is the principle of differentiation under sign of integration. Here x is cancelled out, and we have integral 0 to infinity e to power minus ax cos sx dx. Right? Now, this is your standard integral. You have a formula directly, because you know that the formula e to power ax cos bx dx. Here we have direct formula, that is formula is e to power ax a cos bx plus b sin bx upon a square plus b square. Now you can use this formula directly and you calculate this value. What is the value? That is e to power minus ax minus a cos sx plus s sin sx upon minus a square plus s square limits upper infinity to 0, right? And now substitute the upper and lower limits, then you see the value, that is the d by ds of fs. This is equal to right hand side. If we put upper limit, that is 0, because e to the power minus infinity is 0, right? And this is minus a square means a square plus s square. Upper limit is 0. Lower limit, that is e to the power 0, 1, that is minus a plus 0. Right? Finally, we get a upon a square plus s square. This is your limit of this a upon s square. Now, to find the fs, integrate this. Now, integrating with respect to s, we get. This is the process, this is the trick, this is the method by which you have to solve the Fourier sine transform as well as Fourier cosine transform. Right? This is fs of s, and this is integral a upon a square plus s square ds. Right? This is directly. A is cancelled out. This is directly, you know that the formula of tan inverse s upon a plus constant of integration. Because of take this as equation number 3, because of indefinite integral, and by this you can put when s equal to 0, then fs of s is also 0. Right? So by 2 we get c is 0. Now, finally, substitute this value in equation number 2. We have Fourier transform of this is tan inverse s upon a. That is Fourier sine transform of given function. Right? This is your final answer. This is the final result. This is the method. Whenever in case of Fourier transform, you will get integral which cannot be solved, calculated directly, then you have to use such process. First, you have to integrate with respect. First, you have to differentiate with respect to s. After differentiating, now you will get, because differentiating is with respect to s, and always you have to remember that right hand side there is integration. When you differentiate with respect to x, then in the sign of integral, it is a differentiation, and that is a partial differentiation. And after differentiation, you will get that integral which was firstly, that is lengthy, which is indirect, which cannot be solved directly. Now it becomes easily here. We see that if first we have the integral e to power minus ax x cos sx. That is really solved to, that is impossible to solve directly. So we differentiate this, x term is cancelled out. Then we get the integral 0 to infinity e to power minus ax cos sx, and that is directly formula by you have already in class 12 you have studied this in reduction formula. E to power ax cos bx dx equal to e to power ax a cos bx plus b sin bx upon a square plus b square, and by this, right? Now up to this question I am just leaving this and I am stopping this lecture, and in the next lecture also I will take some results based on the Fourier transform and also some numerical examples of Fourier, because here in today's lecture I took numerical example of Fourier transform and Fourier sine transform, but numerical example based on the Fourier cosine transform is less. In next lecture I will take up this, and then I discuss some other ideas, and then I will come on the second topic, that is the Z transform. Okay, thank you.